Hi, everybody. At NCTM, I saw a problem posed on Twitter, and I think it came from Ruth Parker's session. Um, but the problem involved these bracelet numbers or bracelet sequences. And just to give you an intro of how they work, to get a bracelet, we start with two numbers that are between uh, 0 and 9. And the example that was given was 6 and 3 to start with. All right, to generate the next terms of the sequence, what we do is we add these two terms together and then just take whatever the ones digit is. So 6 plus 3, that gives me 9. All right, and then to get the next term, I add these two together and I just take the ones digit. So 3 plus 9 is 12, while the ones digit is just a 2. And then I continue with this pattern. So 9, 2, 11, 2 and 1, 3, 1 and 3, 4, 3 and 4, 7, 4 and 7, 11, 7 and 1, 8, 1 and 8, 9, 8 and 9, 17, 9 and 7, 16, 7 and 6, 13. And I stop here. And the reason why I stop here is because this 6 and 3 match this 6 and 3. So what will happen after this is I'll just get the same pattern over and over again, which I assume is why they're called bracelet numbers, because they just ring around. Like if you were to put these around your wrist, you'd have a bracelet. It would just be, it would loop. So then I asked myself, what do you suppose happens in the general case? So if I start with two numbers, A and B, what would happen with the pattern? Well, this whole idea of just taking the ones digit, to me, rang a bell with modulos. So modulos are basically just taking a remainder when you divide by some designated number. So if I start with A and B, really what I'm starting with is A mod 10, B mod 10. So in other words, I'm taking whatever the number this is and I'm dividing by 10, and then just whatever the remainder is, that's my answer, or that's my value. So when I add these two together, this is going to be A plus B mod 10, because I add these two digits together, I get 9, and then I divide by 10 and take the remainder. So 9 divided by 10 is 0, remainder 9. All right, and then likewise here, when I add these two digits together, the 9 plus 2, or excuse me, 3 plus 9, I get 12, which divided by 10 would be 1 with a remainder of 2. And so that's how I get my next term. So I realized that this, for me, it made sense to think about these with modulos. So I started to write down all these general terms. I have A mod 10, B mod 10, A plus B mod 10. All right, then I'm going to add these two together. So I get A plus 2B mod 10. And then I add these two together and I get 2A plus 3B mod 10. And I continue on with the pattern, add those two. So I get 3A plus 5B mod 10. Continuing on, 5A plus 8B mod 10. I'm only going to do one more term here. Oops, mod 10. And then the next term was 8A plus 13B mod 10. At this point, I said to myself, hey, wait a minute here. I looked at the coefficients of A. Coefficients, of A. And I saw that the coefficients of A in each of these terms as I went along were 1, 0, 1, 1, 2, 3, 5, 8, and then I looked at the coefficients of B. Maybe I'll spell it right this time. Nope. Coefficients, pardon my spelling, of B, and I got 0, 1, 1, 2, 3, 5, 8, 13. And there's this guy who, even though you don't invite him to the math party, he always shows up. All right, and that guy's Fibonacci. So I saw this, I saw 1, 1, 2, 3, 5, 8, 13. And so now my interest is really piqued. I want to say, okay, what's going on here? And I guess after a while it made sense because it's recursively defined. You're just adding those two together. So Fibonacci, of course, is going to show up. But I wanted to look at, well, I want to see all these solutions. I want to see what's happening with all these bracelet problems. And so what I did is I went to GeoGebra, and I opened up a GeoGebra file. Oh, I'm going to get rid of this slider here, and I said, okay, I'm going to generate sliders that are going to, or I'm going to make sliders that give me the seeds, if you will. So I'm going to make a number A, and I'm going to make it an integer going from 0 to 9. Okay, and it called it N. I want it called A. Ay. What am I doing? Sorry, bear with me here for just a moment. I'm going to clear this up. Okay, well, let me make this first 0 and 9, and I want it called B, and apply. Okay, I got to get rid of this N here. I tell you, these people showing up to my math party. All right, so now I've got A and B, and I'm going to unlock this one so I can move it. Maybe. All right, so sorry for the technical difficulty there. All right. And A is not an integer. All right, give me one more moment here. I'm going to get rid of this. I'm going to create a slider. Call it A, but except I wanted an integer, A. And we want it from 0 to 9. Okay. Now I think I have the sliders I want. So I'm going to set A and B to 6 and 3, just like we had for the example problem. All right, I'm going to adjust my graph here a little bit, which you'll see why in a moment. And I'm going to turn the grid on just because I like having the grid on. All right, so what I did is I opened up a spreadsheet here in GeoGebra, and I said, well, I want to have GeoGebra create these number strings or these bracelet strings for me. And the way I'm going to define them is I'm going to say, well, in A1, and the way we put modulos in is we have to say modulo, and here I'm going to put in A, and then the modulo I want, 10. So I'm taking modulo, this number A, whatever I have it in as a slider, and I'm doing modulo 10. And I have it there. So 6 modulo 10 is 6. All right, then to get the next term, or what I have to do is I have to put in B, right? Because the second term in the sequence was B mod 10. So mod B, comma 10. All right, and then to get every term after that, we just add these two together. So this next one I'm going to define as A1 plus A2, except you have to do that mod 10. So mod A1, comma A2, mod 10, and so now I've got this. Now I can just take this and extend it for however long I want. And I'm going to extend it out to 100 just because that's what I did when I was looking at this. So I'm going to extend it out 100 times. And so now there are my first 100 terms in the bracelet. No matter what I change A and B to, I'm going to find all those terms. Maybe. There we go. So change A and B, and I get the bracelet. Okay. So now I said, well, that's nice, but I still would have to look down the whole list and find where the repeat is. And I'm really bad at finding those kinds of things because I just all the numbers start to look the same. So what I want to do is I want to create a visual that would show me exactly where it happened. So what I did then is in column B, I'm going to put in essentially the second term in the sequence. So I'm going to define B as being equal to A2. All right, and then I'm going to do that all the way down this whole list here. So I've got these 100 pairs of numbers. And the reason why I made this pair of numbers is because now I want to plot them on my graph. Because if I do that, what I'll be able to do is see exactly where the bracelet ends. Oh, and I need to do this. Call that 1. All right, so now let me select all these pairs again. And what I'm going to do is I'm going to generate a list of points. Now I'm not going to include the first one because if that's my seed, I don't want to see that one show up. I want to just make sure that the other ones, that somewhere on the graph, I'm going to get these points. So I'm going to create a list of points, and there we have it. So I've got all these points now. And what we see is that when I have 6 and 3, I get 12 distinct points, which makes sense because I had to do 12 iterations of the initial or of the problem description in order to get to this point. So now what I can do is I can just play around with this and see however many points show up is how many steps it would take. So if I looked at 6-3, I see, oh, well, that's 12 steps. If I look at 4-2, I see, oh, that is, I don't know why that point's showing up exactly. Well, I'll have to look at that C4. I don't know. It should just be 4. I'm not sure why. Oh, this should be a 4 rather than a 1. I see what the problem is because it should really be defined as B98 plus B99. I changed it to the specific case. All right, so modulo B98 plus B99, comma 10. Okay, there we go. Sorry about that. So now, yeah, so when I do 4 and 2, I get 4 points, which means the bracelet would be 4 iterations long. So this has got me intrigued now, and so I start to look at these other patterns here, and I look at, like, for instance, 5-2, and all I have to do is I have to look for the point 5-2 and see what letter is corresponding with it, and it's L2, so that means that it happens at 61. And then I started to look at all of these, and I said, okay, well, what's going on with these patterns here? And so I looked at 7-2, and 7-2 I saw L2 again. And then I looked at some more, and I said, oh, well, let's look at 7-4. And I look at 7-4, and there's L2. So now I start to say, well, what's the significance about L2? L2 keeps showing up. Why is that happening? And it intrigued me for a while. And same thing, like 1-4, there's L2. L2 is always showing up wherever that problem is. And so then I started to look down at this list, and I said, well, if L2 is there, oh, and again, L2, sorry to, I had to count many times through the alphabet, but it's basically at 61 is where we start to see that happening. And every time, no matter what I change the sliders to, I get 1-4, right? And you can see it happening as I go along here. So then I said, well, why is that happening? What's going on with line 61 and line 62 that I always end up with that number? Now, we can see clearly that it repeats, like in the example of 6-3, it happens before this point, but why was it always showing up at this point? And so I decided to phone a friend, and the friend I decided to phone was my friend Fibonacci. So in this line, I decided to define the Fibonacci sequence, so I gave my seeds of 1, 1, and then the next line is going to be equal to A1 plus, or excuse me, C1 plus C2, and then I can just extend this down all the way to, and I didn't really care about the rest of it, I just wanted to see what was happening at 61 and 62, and why I kept getting these. And what I noticed at line 61 and 62 was that my Fibonacci numbers, this one and this one, that were used to generate this pattern, well, I did lots of things before I stumbled upon this. I tried factoring these. I didn't know what was going on. But what I noticed then is that these last digits are 1s. And that's the first occurrence where any two consecutive Fibonacci numbers both end in 1. That is after the first one, or first two digits, first two terms in the sequence. Then I realized that since I'm dealing with modulos, this made sense. No matter what I multiplied A by, if I multiplied it by this number, or no matter what A was, if I multiplied it by this number, I was going to end, and I did it mod 10, I would end up with A. And if I multiplied B by this number, mod 10, I would end up with B. So here I'm clearly going to get my A and B because I've got 1s and 1s as the 1s as the 1 digits of these Fibonacci numbers. So that's why L2 keeps showing up. So I thought that was kind of interesting. And I'm satisfied with that answer as long as I'm looking at mod 10. And so that brings me to my further questions is, well, the first one, what happens if it's a different modulo? What if I'm talking about modulo 7? Well, the problem with that a little bit is then I start to lose the context of the problem. I can't just truncate it so that I just get the 1s digit. I'm dealing with something completely kind of abstract or obscure. And then another question I had that I thought about was, as I looked at this graph, I said, wow, that graph has symmetry. All right, it looks like rotational symmetry about the 0.55. And so then I said, well, what about other graphs? Like, if I looked at this one, 5-4, I mean, which doesn't happen, 5-4 doesn't repeat or doesn't complete the bracelet until that 61st line. And then I looked at this graph a little bit more closely, and I was reasonably satisfied that it also had rotational symmetry, which I thought was kind of interesting. And then I looked at some more graphs, and I said, well, what about 2-4? And as I looked at 2-4, I said, well, this graph does not have rotational symmetry. And I thought, well, that's kind of strange. Like, what causes rotational symmetry, and which graphs have rotational symmetry, which ones don't? So that's a further question. I have to look at it. I haven't explored that one very much at all. And then another question I had was, well, what about these points that don't get hit, right? Like this point 4-7. Apparently 4-7 will never occur in this bracelet. So that's kind of another question I want to explore. And then the last question I thought about was, what would happen if I made a map? Essentially, if I started with the first point and then connected to the second, and then to the third, and to the fourth, and to the fifth, would I see any sort of significant relationships happening there? Especially looking at the graphs that were a little simpler, like the one that had just 12 points, if I saw something that happened with that. So that's where I'm headed with this problem, and I hope to continue to play with it, and I'll share anything I find with you. Thanks.